All right, week two. Let's get into it. Today we're going to talk about everything camera related, how the camera works. And it's going to be broken up into four separate lectures. First one, we're going to be covering the camera and the lens. Then we'll get into ISO, aperture, and shutter speed. Then we'll break down the light meter. And then lastly, we'll cover the beautiful thing known as the histogram. So pull up a chair, pour some coffee, and let's crack into it, huh? It's not really spam. Spam's gross. Yes, that is correct, Batman. Get it in camera. Now, as funny as this is my favorite place to start in a digital class because this idea of fixing it later in Photoshop is ridiculous. That's not this class. Photoshop is great. Fixing it in post is nothing new. We saw that with Riegelander in the history of photo. People have been doctoring photos for ever since, well, 1826, let's be honest. But this idea of just shoot hundreds of photos and ones will come out, that's not true. Fix it in post is just a terrible idea. Get it right in camera. Understand your settings. If you know how to balance your light meter, if you know that dance between ISO, shutter speed, and aperture, you'll know how to make a good photo. And that's what this class is about. Learning how to get it right in camera. Now, absolutely, we're going to use post. We're going to edit every single image. You'll never just turn in a raw image. There's always something that needs to be fixed. Highlights, shadows, midtones, one thing or another. And we're actually going to be using Lightroom, not Photoshop. So sorry, again, boy wonder, double slap maybe. But keep that in mind. Get it in camera. So this is your camera. These are the parts of the camera. This is if we took a camera and cut it in half. This is what it would look like. And this is the same both for our digital cameras and our 35mm film cameras. Light is light. Light works the same. And they're both based on the same idea of the single lens reflex. And what that means is that lens can come off, and we have this pen and prism inside that light travels through and it hits a mirror that bounces light up to another mirror and then bounces that down to another mirror and then out through your eyepiece. So all of that wonderful mirror happening gives us the world outside right side up and right oriented. Without all that pen and prism, we would see everything upside down and backwards. And also this makes a really neat Fantastic Four logo. Look at that. Really, really awesome. When we hit our shutter button, which that's what this is, the mirror gets out of the way and that engages the shutter to open and close for a predetermined amount of time. And light just travels straight back and is recorded either on our sensor or our film plane the exact same way. There's nothing different. Light is light. You can see our lens is made up of a number of things of glass that are both concave and convex, and this is for sharpening, increasing our resolution. The better the glass, the more expensive your lens is, but also the sharper your image will be. Now this is what it would look like if we actually did this to a camera. We actually cut it in half, and this is, actually an older camera, much older. Everything's been streamlined, but you get the idea. You can see how much actually is part of your camera. You can see all of the little computer that is involved in making everything work. But you see, here's our lens. You can see that glass for real. You can see how light travels through here. It hits this mirror, and then it goes up to another mirror, to another one, and then out through our eyepiece. Now this is for our DSLR, our digital single lens reflex. Our mirrorless cameras, although it does have an eyepiece, the eyepiece is a digital projection. It's like a TV screen. And the back shows the same thing. So this is the back of the camera, and this is also another screen that you can see. You can shoot live view, and what live view means is when you look through the eyepiece or you look at the back of the camera there, it's showing you what's in front of the lens. But it's all a digital projection. The advantage of our DSLR is it's real world, and everything looks real. But if you like watching a TV screen, mirrorless is the way to go. But again, light works the exact same way on both of those two makeups. And one way to really think about how light works and how our cameras work is to think about how they equate to each other in the form of our eyeballs. Lenses and cameras work the same as our eyeballs do. Both have a front lens. Both have a hole through which light travels through. And that light is also recorded on the back plane. And it's, in both of them, recorded upside down and backwards. Now, when we shoot film, we correct for that when we develop our negatives, and then we make our prints the way we position our negatives in the enlarger or scanner. It compensates for that flipping of upside down and right side right. Our eyes do the same thing, but our optical nerves crisscross, and this compensates and corrects for the upside down and backwards, so it doesn't look like we are walking on the roof all the time. But from the beginning, the best way to think about how your camera works is it works a lot like your eyeballs, although our eyeballs are much more advanced, and we can see in much lower light than our cameras can. Keep that in mind. That'll make sense when we do shutter speeds. This is a wonderful handout slide to definitely come back and reference. This breaks down pretty much every piece of the camera, everything you'll need to know, where to find, how to adjust things. And of course, every camera company has their own proprietary makeup, but they generally work the same, and they're generally all set for right-handed folk. So left-handers, again, sorry, but our shutter button is always going to be on the right-hand side by your right index finger. And then the turnstile here, either for your shutter or your f-stop. This is an older version. Some have one for both. There might be two buttons you need to hold. But the general makeup is exactly the same. So this is a real slide of a real camera. And this is showing what live view would look like. Now this is a DSLR, but this is referencing what it would look like if you had a mirrorless camera. And the mirrorless means that there's none of that internal mirror. So when you look at the back of the screen, you're generally looking at what the lens sees, and it doesn't have that whole mirror system. So it cuts down on product. They're cheaper, they're lighter. Well, not necessarily cheaper, but we'll get to that. And you can see how our camera compensates for this upside down and backwards. We see this wonderful unit on the back of the screen here, right side up and right orientation, the same way as it is in front of the lens, as opposed to being upside down and backwards. And it's because the computer compensates for everything. It fixes the orientation, and it also captures the color. Now, the back of your camera also has a bunch of other buttons that you need to familiarize yourself with. And again, they're all different. This one's a Nikon. Your Canon's going to be completely separate. A Fuji will be totally different. Sony, Pentax, whatever you have, it's going to look a little different. So all these buttons will do something different. And a number of times one button will do multiple things where you can hold another button to make them do something. But generally what you see here at the bottom, you'll also see through your viewfinder. Now the way this works in a DSLR is obviously we'll see the image or place in front of us, but also at the very bottom of your viewfinder you will see your shutter speed, your f-stops, your ISO, what kind of metering you're in, or what kind of mode you're in, and all of that will make sense a lot more coming up. So all of your cameras also have a menu inside, and the menu has a ton of options. Familiarize yourself with everything that's in the menu, because you will need to know how to adjust all these controls. First and foremost, image quality. We want that on RAW. Now, image quality refers to the file size, and image quality is pretty straightforward. The higher quality is going to be your RAW image. That RAW captures everything as much as possible in front of you, and it makes a giant file size. A JPEG is a compressed file version, and it dumps as much information as possible and compresses it down so you have more room on your memory card. We're using a non-destructive editing program. We want to have as much control as possible, so get into your menus, find out how to change that image quality to RAW. Now this one has RAW plus F. What this means is it's actually recording two files of the same photo. RAW being the digital negative, and then F means it's a fine JPEG. Depending on your industry, this may come in handy, but for now, all we need is RAW. And once you select just RAW, image side will be grayed out. And again, this is a Nikon menu. Your Canon's going to look different, but you're going to have the same options. White balance is something we will get into. We can change the color tonality, the temperature actually of our images, and ISO. We will be setting ISO. So you want to make sure that your ISO is not on auto. So those three things are very important: ISO, white balance, image quality. Make sure you get into your menus and find out how to change those. And you'll need memory cards. So this was the huge breakthrough with digital. This was what everyone went crazy for, is not having to buy a bunch of film, not having to get wet and develop film, and the ability to reuse these. So these are some of the standards. Generally, most people are going to be using the SD, the secure digital. That's what we have in our prosumer, like your D610 or your 70s, those kind of models generally take this kind of memory card. The compact flash used to be thought of as, you know, the big boy, and it was for the higher end cameras, and it still is. I believe your 5D Mark, whatever Iron Man is on at this point, it still takes those, but it also takes smaller ones. So you will need the correct memory card to go with your camera. And for this class, generally you can get away with one. Typically I have a few on hand. Anything that's electronic will fail at some point. These are really small. These are really easy to forget in pockets. These are really easy to go through the washing machine. And the price on these have really come down a lot. So generally I have about 4 with me, and I rotate them all the time. And the memory card, this is your storage device. This is what we're going to record our images on. You're going to want to format that. So there's another thing you need to find out in your menu. Once you put your card into your camera, you'll need to format it. And that generally it's erase. It's like deleting everything off the camera. But then it introduces that card to the camera. So they're all in one in unison. Now these are storage devices for shooting. Don't use these as long-term storage devices. That's what our hard drives are for. So when you do a photo shoot, you have your memory card, you put it in your camera, you format it, you shoot, you come back to your computer, you copy the information off, and then you're actually going to put that memory card back in the camera and reformat it. And that's the best way to delete your images. Images are recorded in camera. It's easiest and it's best to keep any kind of truncation away by formatting in camera. Now there's this one called this micro SD. This is a small one. You see these in cell phones or the GoPros and things of that nature, and those are great for that. You can also get an SD card that is a go-between, but I don't suggest that. It's like when you plug in extension cord after extension cord after extension cord, you know, the electrical unit's going to break down. Just buy the inherent card, put that in your camera, and use that. Save these for the cameras that they're necessary for. Don't use the go-between. Too many times I've seen them fail, and students have lost images, so keep that in mind. Another thing you'll see here on the memory card is you see this 60 MB and then S. So this means 60 megabytes per second for the read-write speed, whereas this one says 150 megabytes per second. So this may be larger in size, physical size, but this is actually a slower reading, slower writing, and it's actually a smaller size altogether. So 32 GB means 32 gigabytes. That's the max amount of information this can record, whereas this SD is a 64 gigabyte. That's a lot of information, and it reads relatively fast. So this means you can absolutely have plenty of room to record those raw file formats, but also it's going to happen, it's going to read and it's write very fast. And what's good about knowing this, your megabytes per second, is if you're shooting film, if you are shooting video for a film, that makes more sense. You're going to want as fast read-write speed as possible, because due to buffering, if that fills up, the camera will stop recording, and it may be at a point where you don't want to make a pause. So something else to keep in mind. So our cameras all have image sensor. So our information is recorded on our memory cards, but it's being transferred from our image sensor. And our sensors are made up of pixels. And a pixel is just a small little unit that records information. And our cameras are rated in size of megapixels. And 1 megapixel is actually 1 million pixels. So if a camera says it's 25 megapixels, it's roughly about 25 million pixels. Generally, the idea for now is the more pixels, the better. Also, typically the larger your sensor size. So the larger the sensor size, the more megapixels, the more information, the sharper your image is going to be. Also, the larger your sensor size affects something that's called depth of field. The larger your sensor is, the more depth of field you will get. We'll get into depth of field later, but there are 4 aspects that control it, and the sensor size is the first thing that we've come into. So full frame cameras are equated to our 35 millimeter format, and they're on our DSLRs, they're considered the largest, the full frame. And then we also have crop sensors. And a crop sensor is just that. It's cropped in on part of the sensor. Now we'll get into how that works with our lenses, but generally what a crop sensor means is that sensor is not the exact same size as our full frame. So you could have a 25 megapixel crop sensor and a 25 megapixel full frame sensor. And inherently, the full frame sensor will give you a sharper and a deeper depth of field image. So again, let's talk about file formats real quick. So before you start shooting, and again, you need to set your file format. You need to know what kind of sensor you're shooting on. And JPEG is a standard. And it's fast, it's quick, but it is a loss type image because it is a compressed file format. The camera essentially shrinks down your image to something smaller so it can save space on your card. Whereas our camera raw, also known as DNG, which stands for digital negative, is uncompressed. There's no compression at all. It does take a lot more space on your memory card, but it gives us the most precise control when we are editing in post. So Camera Raw is the proprietary digital negative format for each company. So Canon has one, Nikon has one, Pentax has one, Fuji has one. But then there's also the open source. The public available is the digital negative. And you'll see this when we get into Lightroom. But basically, DNG, Camera Raw are the same file format. TIFF is uncompressed, but it's not the same as a digital negative, but it is uncompressed as well. And a PSD is Adobe's proprietary format. And if you've ever worked in Photoshop and used layers, you know, if you save a PSD file, you're saving everything. So, but PSD is not, it's not a choice for us in camera. We only have JPEG and RAW, I believe. So we're going to go with RAW. All right, so your sensors are made up of photosites, and that's what actually your pixels are. These little squares called a photosite, and a photosite captures, you know, red, blue, and green, and it actually has more green because our human eyes are more sensitive to green. We see a lot more green, so the sensors themselves have more green filter on them to capture as real as possible. And you see in this image on the right, that circle where it's all blown up, it's zoomed in very much, you can see those little squares. That's what our pixels look like. They are those little squares. They're really jagged, they're really rigid. And also you see this illustration where we have that lens in between. You can see that the image that is projected on the sensor is actually upside down and backwards. The real, quote unquote real, on the left hand side of this mother holding this child is right side up. And this is, again, just showing how our camera records information, and due to our computer processors, our cameras just switch everything right side up. So another thing that's our digital code is called bit depth. And bit depth is basically how much information your camera can store for each channel in the pixel. So an 8-bit color depth photo is just a bunch of ones and zeros strung together, and it has 256 values per channel. So if it was a black and white image, it has 256 tones. If it's a color image, it's got 16,777,216 total colors. And this is much less than what we can see with our human eye, but this is plenty, actually. We can see, this is enough to trick us. So a 1-bit image would look like this photo of this parking lot. It would just be 2 tones. It's only black and only white. A 2-bit image is 4 tones. It's got that black, it's got that white, and now it's got 2 shades of gray. And then our 8-bit here is a 256 tonal values. So this looks like a full tonal range to us. And when we put that in color, there we can see that 60 million plus colors, and it looks real, and it looks natural. So our pixels are made up of photosites, and they're bits of information. The more bit, the more information. And then we also have something that's called pixels per inch and dots per inch. So pixels per inch refers to how many pixels per inch there are in our digital file. And our standard for resolution is 300. And what that means is 300 pixels per inch. And here's a photograph of these martinis in a low light on a table at 300 DPI. Sorry, 300 PPI. So PPI is in camera, and DPI, dots per inch, is when we are printing. That refers to how many dots are laid on our printer paper per inch. Again, more dots, more clarity, more sharpness, as opposed to this image, which is 72. So 72 is fine when we are working on the web, actually. In fact, these images that we're looking at due to processing are at 72 pixels per inch because we don't need that much resolution. But when we are talking print, we need more resolution. So this is what a photograph would look like if we printed it out at 72 DPI. At 8 by 10, it would fall apart. And by fall apart, I mean this was supposed to be a circle, and now we can actually see those pixels that we saw in the previous slide. We can see them start getting rigid. You can see the squares. We can see that the clarity and the shadow now is getting kind of muddy compared to our original photo, where it's much more fluid. So inherently our cameras are shooting, I believe, about 240 PPI. So we're getting a lot of information. That's the standard in our Canon cameras. When we get to printing later, we'll talk about exporting at a certain pixels per inch as well, when we're going to export at that 300 DPI. So focal length. Focal length refers to the distance from the lens of optical center to the image plane when the lens is focused on infinity. And this is what we rate our lenses at. So we know, or you've probably noticed, that your camera has a lens on it, and that lens probably says something like 50 millimeters, or it says like 35 to 75 millimeter. And that's literally measuring that length, the distance of the focal point at infinity to the image center. That green line represents is that actual physical distance. And that length is what we rate our lenses at. So the perfect lens on a 35 millimeter film format, so our DSLRs are considered the same format as our 35 millimeter film cameras, and our lenses and our lens lengths all equate to one another. So the angle that is the standard that equals the human eye is actually the 50 millimeter lens. And so what that means is what we see as sizes and spatial difference and distortion with our eyes is roughly the same as what we see on an image that's been captured with a 50 millimeter lens. Anything shorter than a 50, that lens produces what's called a wide angle. So it makes the perspective of the world look wider. It makes everything look bigger. It pushes things further away. Anything longer than a 50 is a telephoto or zoom lens. And what that means is it makes subjects, places, objects look closer to you than they are in the real world. Both of these warp perspective, and they both look different than what we see with our human eye, where the 50mm lens, those images look normal, quote unquote normal, as far as how everything is spaced out. Anything on a wide angle is going to look pushed away, it's going to look bigger, it's going to look stretched out. Anything on a telephoto is going to look closer, it's going to look a little more compressed. So here's a range of lenses in comparison to one another. All shot at the same spot, all shot on the same camera. The photographer just switched out the lens. And we can see, if we look at that 50mm lens, that second row, second from the left, second from the right, third from the left. Everything looks normal. The lake, the distance from where we are at the lake to the harbor, to the boats, to the mountains, it looks generally normal. But if you look right next to it, that 24mm, now everything looks much further away. We can now see the bank of the lake there, pond, whatever it is. And then the distance from us to that harbor looks much further away. And if you go directly above that to that 12mm, oof, it's huge. Everything looks way, way pushed further away. It's a really long swim. It looks like it's a cold swim too. I don't know, maybe it's just me. But that wide angle lens is super wide, and that mountain looks really, really small. You compare that to the 50mm, mountain looks a little bigger, and everything looks a little closer. So if you go right under that 50mm to that 300mm photo, that harbor, those boats look a lot closer. In fact, they all look really close to each other. And that image is so zoomed in, we don't see a mountain range at all. It's so cropped in. If you look at the spatial difference between the boats and the docks and that red building, they look very much like they're right in front of each other, right on top of each other. If you go right next door, look, in this 500mm, there's someone standing in that boat, really zoomed in, really close, very compressed, very, very compressed. If you look at across this other harbor to these other boats, they look as though they're right next to each other. And in that 50, look, there's a good distance, a very good distance. Here's another slide, same thing. Now we're in the city, and you can see the camera and the lenses. You can see the angle of view, and you can see, starting with this wide angle, how much more compressed those images get, and how zoomed in you get. On this 1000mm, that is a giant lens. You can see where we were standing. This photographer zoomed in way, way over into that building. And look how compressed that space looks. It looks as though this building top is right in front of another building when there's a good wide street in front of that. So your lenses, definitely something to think about, because whatever lens you use, it's going to warp reality, or it's going to make things look relatively normal. What's real important about that is when we're talking about portraits and people, we typically do not use wide angle lenses for portraits because it warps everything. It makes everything look wider. It stretches things out. People typically want portraits, to capture either what they look like or look a little better. And our zoom telephoto lenses compress space a little bit, makes things look a little nicer, or at least nicer in comparison to the wide angle. Like, this is just a mannequin's head, but here on these wide angle lenses, the face is really stretched out. Looks very fake. Here in these portrait lenses, this 85mm and this 200mm, they are a little bit cleaner. They look a little bit more normal in relation to each other. So a zoom lens is a lens that gives you an option of multiple focal lengths. So like I mentioned before, you may have like a 35 to 75 or 24 to 120. And what that means is that lens can change that focal length. It can change the distance from the back of the lens and the focal point to the sensor plane. This slide is demonstrating that. If you were in one spot and you had a zoom lens, the difference of images you can make from wide on the outskirts all the way zoomed into just that gentleman in the doorway. This is great. These are great opportunities, especially if you're a street photographer, having those options. One thing to keep in mind though, the cheaper lenses that are zoom lenses, they're rated in different f-stops. So it may say something like 3.5 to 5.6. And that's referring to the quality of glass. If it's not rated at one f-stop, then as you zoom in, you're losing stops and you're losing a little bit of clarity in that image as well. So keep that in mind. But there's definitely an advantage to having these zoom lenses where if you didn't say necessarily like this person, but you didn't want to get close, well, that's kind of mean. If you didn't want this person in the photo, but you didn't want to get closer to this gentleman, you could simply just zoom in using your telephoto lens. And this is an extreme detail difference of one that goes from super wide to really zoomed in. And you can see how different effects, different photographs you can get from different focal lengths. All right, so let's back up to sensor sizes and how sensor sizes work with our lenses. So a full frame, again, is a camera that has a sensor size that is equal to the 35mm format of 24mm by 36mm. And this is the standard size. A crop sensor is smaller than that. And our mirrorless cameras have sensors that are smaller than that as well. And you can see this as far as how sensor sizes relate to each other here on the right hand side, this big full frame. And then you can see our crop sensors are micro 4/3. This is our general standard in our mirrorless, and then our iPhone. And again, coming back to pixels per inch, our PPI, you can see if we have 25 megapixels spaced out over this, it will look a little cleaner than if we had 25 megapixels all jumbled in this small sensor. Just something to keep in mind. So the way lenses work on our full frames, if you have a full frame camera and you put on a 50mm lens, you are using a 50mm lens, the full frame, as you would if you were on a shooting film. If you put that 50mm lens though on a crop sensor, you're actually only using a portion of that lens. So on this slide on the left hand, the outside of the frame equals our full frame, and this is everything you would see here at Yosemite. But if you're in this same spot with a crop sensor here in this green frame, this is all you would capture. So you're missing all of this information. So you're essentially cropping into the lens. And our crop sensors always tell you how much they are cropping in. So this is a 1.6, this is a 1.5, this is a 2 times crop sensor. And what that means is you multiply the lens focal length by that number, and then it gives you the approximate lens you are using. So if you had a 50mm lens and you were on a 1.5 crop sensor, you would multiply 50 by 1.5 and you'd get 75. So that lens essentially is working like a 75mm lens. Alright, so let me show you a little bit more about this. Let's go ahead and draw a lens. So that's your lens. Well, essentially that's your lens. And if you notice, all of our lenses are round, but our photos are a rectangle or square. Why is that? Well, it's because we're using a portion of the lens. Now our full frames use as much possible from our lenses. They go edge to edge. And everything inside that rectangle is what is our photograph. Now there's a little bit on the outside that we don't capture, and that's fall off, that's fine. So if this was a 50mm lens on a full frame sensor, we're using as much possible of that 50mm lens. But if we had a crop sensor, now our sensor is only this big. So we are only using that much of our lens, and so all of this is not being used. So we are cropping into our lens. So if this, again, in that same scenario, is a 50 on a 1.5, this 50 now becomes a 75 millimeter lens. Does that make sense? I think so. Should. So here's another example. This just seems to be something that trips up a number of people about sensor sizes and crop factors. Again, just to further illustrate, the yellow border is our full frame sensor, and then interior here on this white border is our crop sensor. And you can see in this scenario, in this landscape with this lighthouse, a full frame, we're getting all of this water, getting all of this sky, but our crop sensor, we're right up on the shoreline and right up on that lighthouse there. So it's important to keep in mind when you are shooting with the crop sensor. Now, a best camera to use is the one that you have. You know, sure, a full frame gives you more information, but if you have a crop sensor, that's totally fine. It's about being creative. It's not about megapixels and bits and all of it. We'll get into that later. So here's an example of some images and showing you correlating what lens they were photographed on. And this is just a normal 50 millimeter lens. And you can see spatially everything makes sense. The distance between this backboard, sports ball, the backboard of this basketball hoop, distance to this light pole, to this tree in the background, to these clouds and the wires, all looks normal, as if we were there. Looking at this spatially, everything makes sense. Now, same lens, interior, the distance, these leading lines and these vanishing points, all spatially make sense to our eyes as far as the bricks and the wall and everything that's in here. Size-wise, we feel as though we fit in here because of that lens. So zoom lenses, again, they pull everything closer and they compress space. So here in this dragon boat race, you can see all of these people, working very furiously, paddling. And you get some really great expressions. And the great thing about this zoom lens is, the photographer was a distance away, so they could capture all this. But if you look at these boats and the people, they feel as though they are stacked on top of each other. Now, logically, there's a little bit of space, otherwise they're hitting each other, right? But in this photo, because of the lens, they're all really compressed. Same on this one with the Queen Mary in front of New York. The stacks on the boat, they look as if they're right on the sidewalk, right in front of these buildings. Again, it's that long lens. It's compressing the space. It gives you the ability to photograph at a distance, but then photographically, optic-wise, it pulls everything closer together. Compared to the opposite here now, the wide-angle lens. The wide-angle lens makes everything look bigger, makes space look bigger. This is a good one, if you've rented a hotel room or an Airbnb and you see the space looks really large at 300 square feet. Then you get there and it's really small. It's because they photographed with a wide-angle lens, and you can tell by look at how large this bed in the foreground looks. There's even a little bit of curvature here in the corners. Same thing here, this interior space. These books, they're in the foreground, they look really big, but you can see there's a bit of a distance, like it recesses really fast. You can also see that there's a curvature in this candlestick holder that should be straight, but it's got a little warp to it, and that's because of the lens itself. And now, super wide angle are our fish eyes, and this is an extreme example of that fish eye lens. Well below this rider and bull, you get everything, but you absolutely see this crazy warping, and that's all due to the optics of the lens. Another real manipulated one is a macro lens up close. You should note that your lenses have a distance where they won't focus. Again, just like your eyeballs. There's a certain point where you can't focus. Cameras are the same. Lenses are the same, unless you have a special lens. This macro lens allows us to get really, really close to see, these extreme close-ups. popular in like dioramas where you can get really, really close on this praying mantis eating this human being, which of course is, it's a small figurine. But keep that in mind. If something isn't sharp, not focused, maybe it's because you're too close. Another thing that we need to keep in mind for our lenses is that zoom. Now, we see two different options here, two different examples. We see an optical zoom and a digital zoom. So the optical zoom is where we can actually change the focal length, like on our telephoto lenses, where you can physically move that focal point. Optical lenses remain sharp. It's like swapping out a lens. Like if you had a 50 millimeters and you took that off and you put a 300 millimeter on, it's an optical zoom. A digital zoom is just blowing something up. And it's something that we all do. I'm sure we all understand this now on our iPhones and our iPads, where you pinch something and to make it bigger. And as you do that, you see it fall apart. It gets blurry. So that's what a digital zoom is. It's not actually getting any closer. It's just expanding the photograph. And as you do that, you pull the pixels apart. And that makes it look blurry and out of focus. Here's another example of that. Here we see our standard 50 millimeter lens. Everything's nice and sharp. Down on the bottom we see someone in the same spot making a photograph with a 200 millimeter lens. Now much closer we can see that road up close, but both are really sharp. So this center one is not an optical zoom, I'm sorry, is a digital zoom of the 50 millimeter, where they just cropped in on this. And you can see as it completely fell apart, got really blurry. It looks more like it's a frame from an earlier Call of Duty. Looks very animated. It's not real. So keep that in mind when you're shooting with these digital cameras. Some of the mirrorless ones may say optical or digital zoom. Optical is the good one. Digital zoom is not. And then a couple more things when we're talking about the camera bodies and the lenses. Your white balance. So another great thing about digital is that we don't have to change our color film. Color is due to light. Light is actually a temperature. And so the differences of light give off different temperatures, and these different temperatures give a different color cast. So our cameras, we can adjust our color temperature depending on what kind of lighting situation we are in. So incandescent is your old tungsten. Fluorescent is like typically in like schools and office buildings. Sunlight is of course sunlight. Cloudy is a cloudy day, and then shade is in open shade. And on your camera you can adjust your white balance to whatever situation you want to give you the best possible color tone. And this is great for when we get to post. It cuts down a little bit. But the great thing about shooting in RAW, a little tidbit here, is if you are in the wrong white balance setting, when you get into post, we can change this fairly easy. So some specifics, something as simple as holding your camera. This is the standard way to brace your camera for most stability. And of course, one of the most important parts of your lens is where to focus. So know where your focus ring is. That sets your focal point. And then how to focus. So when you're looking through your viewfinder, either your viewfinder or your live view in the back of your camera, there will be these focal points. They're either squares or rectangles, and whichever one is the focus indicator will illuminate. And when you are in manual, you manually adjust the focus ring, and you'll see the photo or in front of you get blurry and then sharp. And then of course when it's sharp on one of those focal points, whatever you're focusing on is what will be sharp. Now when you're in auto, and this also works for when you're in manual as well, you press the shutter button halfway down. Now if you press the button all the way down, it's going to take a photograph. But if you press it halfway down, it wakes up your camera. And it's just like our computers and our cell phones, they all go to sleep. Well, your camera goes to sleep too. And the way you wake it back up is by pressing the shutter button halfway down. And when you do that, it ignites the focal. and it also starts up your light meter, which we'll get into later. But when you're on automatic focusing, when you press it halfway, the camera will try to focus on whatever is in front of it on one of those focal points. And if you don't like that focus point, you can readjust and then press the button halfway down again and it'll refocus. Now, if you are in a situation where it's either really, really bright or you're trying to focus on a solid color, autofocus isn't going to work because autofocusing is looking for contrast. So wherever you put that focal point on, make sure there's a variance of tone and light and line and shape. Otherwise, you're just going to see that photo go in and out of focus. So depth of field. So depth of field is what is in focus from foreground to background. And your depth of field is broken up into basically thirds. And when you set that focal point, you're actually focusing 1/3 of the way into your photograph. And so everything that's 1/3 in front of that focal point will be sharp and in focus. And then the rest that's 2/3 behind it will be sharp and in focus. It's what's called hyperfocal. And the focal point just sets the focus point. We're going to get into more of the depth of field in the next section when we get into aperture and some of the difference of lenses. So here's two different examples of some depth of field. The one on the left is a deep depth of field where everything is in focus. Either the sculpture is in focus, the background is in focus, the columns are in focus, another obelisk in the background is in focus. And the one on the right, that depth of field is really shallow. It's just focused on that sculpture's eyeball of the dog. Another thing to point out too when you are focusing, going from autofocus or manual focus, remember to focus on your subject. And this is another thing that happens a lot with our autofocus is if it's in the dead center but your subject is on the left, it may entirely miss your subject and and focus on the background. So as we see in this photo of this gentleman in the library, the autofocus went directly to the books and ignored him. So to correct this, the photographer simply just moved the camera so that the focal point is on the gentleman, held the button down halfway to get that focus, kept that pressure, and then reframed, and then pressed the button all the way. And that's how that photograph was made. All right, so one down, how the camera works. Lecture 1, camera and the lens. Here's some examples, real world too. We can see here's our DSLR. Here's our mirrorless camera. As we see the back of our, oh, it's pretty dirty, look at that, of our DSLR. The viewfinder, when we look through the viewfinder, we see the real world. And our mirrorless, there it is. It's all digital, but also does have a viewfinder. And there's certain settings that it will eye detect, which is pretty neat. It's pretty neat, yeah. Either one, everything that we just talked about works the same. There's some little differences, but for now, that's how it is. So how the camera works, camera and the lens, there it is. We'll get into aperture, ISO, and shutter speed next. So see it a little bit. Now it's cold.